Welcome back, everyone, to part 2 of our theory and intuition discussion behind principal component analysis. The relevant and suggested reading is section 10.1 of ISLR, which covers the topic of PCA. Now, principal component analysis operates by creating a new set of dimensions, that is, the principal components, that are simply normalized linear combinations of the original features. That is to say, if we have some original feature data set of x1, x2, x3, and so on all the way to xp, then the first principal component, for example, z1, would just be a linear combination. That is, some coefficient times x1, some other coefficient times x2, and so on. So we've seen this example before. Let's imagine we have a two-dimensional data set, feature 1 and feature 2. We could eventually discover the first principal component, and that would be equal to a linear combination of some coefficient times x1 plus some coefficient times x2 to get z1. And eventually what we want to be able to do is, using that principal component, is perform dimension reduction. So from two features, we would essentially project everything down to that z1, that first principal component we found, and then upon that projection, we could now line everything up, and we've gone from 2 dimensions to 1 dimension along that principal component. So z1 is now just a linear combination of x1 and x2. So it's taking some information from x1 and some information from x2. If we went from 3 dimensions down to 2 dimensions, it's essentially the same thing. Here we can see points in some sort of 3D space, and we could discover the first principal component and the second principal component, which essentially makes a 2D plane, and we could project those points down to the second and first principal component space, and now you've gone from 3 dimensions down to 2 dimensions. Okay, so the question arises, how do we actually calculate these components? What we're going to do is walk through the steps visually for a simple example. We're going to begin with a 2-dimensional data set. So this 2-dimensional data set has feature x1 and feature x2, and it's 1, 2, 3, 4, 5, 6 along x1, and then a variety of values along x2. And if we were to plot this out, you notice it kind of looks similar to the original feature set we saw there. It's kind of diagonally going up to the right. So the first step in principal component analysis is to standardize the data. Now we already know how to standardize data using standard scalar from scikit-learn. But it's important to actually think about what's going on when we perform that standardization. Essentially, all we're doing is we're shifting the mean of the entire data set to 0. So the way we do this, if we were to show this graphically, is for each feature, what we would do is calculate the values for that feature and then calculate the mean value along each feature. So here we have the mean of x2, that is along the y-axis, and we would do the same thing along the x-axis for x1, for example, calculate the mean value there. And once you have the mean value for all the features, you essentially have discovered that mean or center of the data set. And recall, we want that mean or center to be at 0 for all the columns. So what we're going to do is we're essentially going to shift over the data set until that center is now at 0, 0. So keep in mind the relationships between each of the points hasn't really changed. We've just shifted over the data, so it's now centered around 0, 0. And that's what standardizing essentially does. And we've seen it here now visually. So the next step is to calculate the covariance matrix for the data. But before we talk about covariance matrix, I want to talk about just linear transformations in general, and then we'll hop back to understanding the covariance matrix. So what are we talking about when we need to do a linear transformation of data? Which we already know, principal component analysis is essentially just a linear transformation of the original feature space. I can imagine that I have a point at 1, 1 in my original feature space, and if I were to perform a linear transformation, what I'm essentially doing is I'm multiplying it by a certain set of values, which we could think about in the form of a matrix. For example, I can have this matrix A1, B1, and A2, B2, and perform a linear transformation that would look like this. My original point of x and y would get linearly transformed. So I have A1 times x plus B1 times y, and then A2 times x plus B2 times y. And obviously we could extend this to n number of dimensions. So this should look really similar to the equations we just showed for the original linear transformation principal component analysis. So we would then up, in this case, if the point was at 1, 1, linearly transformed, it would now be at point A1 plus B1, along the x-axis, and along the y-axis it would be a point a2 plus b2. So, how does this actually affect vectors? Well, we understand that a point could be performed as a linear transformation, and it would be the same thing for a vector. After performing linear transformations along a vector, you could get the linear transformation of the vector pointing in a different direction, as well as having a different magnitude completely. We can also think about this as a linear transformation of kind of a plane of points, where after a linear transformation occurs, maybe it ends up being stretched out, as we just saw the 1, 1 point get further moved up to a1 plus b1, comma a2 plus b2. All right, so there's something important to note here, that when you're actually performing these linear transformations, there's going to be a set of vectors for each dimension that actually will continue to have the same direction. So for most vectors, pretty much all of them, when you perform a linear transformation like this, they're going to end up pointing in a different direction after you perform the linear transformation. But for each dimension, there's going to be a set of vectors, or one single vector in particular, that is going to end up pointing in the exact same direction that the original nonlinear transformed version of that vector pointed in as well. So even after this stretching, so to speak, of the original space, your vector is pointing in the same direction. And so that's actually going to be called a special case of the vector, which is an eigenvector. And that contains the directional information, because the eigenvector is going to be pointing in the same direction even after a linear transformation occurs. For example, here I have point vector at 1, 1. So it has 1 along x and 1 along y. And if we were to do some sort of linear transformation and the resulting vector was described as 2, 2, that's essentially pointing in the exact same direction. We can see it has a slope of 2 over 2, which is the same slope as 1 over 1. So this is now an eigenvector because even after the linear transformation, it's still pointing in the same direction. The thing that's different though is the magnitude. So in this example, the linear transformation has created a vector from 1, 1, that is 1 along the x-axis and 1 along the y-axis, into a vector 2, 2, which is going to be 2 along the x-axis and 2 along the y-axis. Keep in mind, these are pointing in the same direction, but now they have a different magnitude, that is the different length of that vector. So what will the actual magnitude be? That's just the Pythagorean theorem of a squared plus b squared is equal to c squared. So we'd have on the left-hand side 1 squared plus 1 squared, and take the square root of that to get the length of that vector, or the magnitude of it, square root of 2. And on the right-hand side, we can see it ends up growing larger to a square root of 8, but they are still pointing in the same direction. Now, for every eigenvector, there's going to be an orthogonal eigenvector, which essentially just means it's perpendicular to the eigenvector. And we're going to be able to discover an eigenvector for each dimension of the feature data set. That is, essentially, for every single feature dimension, that is x1, x2, x3, x4, and so on, there's going to be an eigenvector that, after you perform a linear transformation, would correspond to the principal component. So keep in mind that an eigenvector is just a linear transformation. So what we end up doing is we use the covariance matrix, and we use that to apply a linear transformation to your original data set, and that results in the principal components, which are essentially your eigenvectors. So the covariance matrix would look something like this. It's essentially your variance along one dimension, and then your covariance along x and y. Now, this is a very simple covariance matrix because we'll only have 2 features here, but this could easily get expanded out to n number of features. But what you end up doing is you apply this linear transformation with this covariance matrix, and that will help you discover the eigenvector, which is the vector that would have the same direction even after that linear transformation. And then recall that you're going to end up having an eigenvector for each original dimension of feature data. And so what you're going to be able to do is use the eigenvalue to calculate the magnitude of these vectors, which would also correspond to the variance explained. So we have our principal components, which are those eigenvectors, and the eigenvalues would measure the variance explained by each of these principal components. So what we end up doing is we choose some subset of those new principal components, that is the eigenvectors. And for example, if we wanted to reduce from 2 dimensions to 1 dimension, we would grab the principal component after we sorted it out based off the eigenvalue. So we would choose the one with the greatest eigenvalue because that's the one that explains most variance. And then we would project the original data points onto that new eigenvector, and that's our first principal component. And now we've gone from 2 features to 1 principal component, otherwise saying from 2 dimensions down to 1 dimension. And then we could rewrite this as the first principal component. So the PCA steps written out are to first get your original data, second calculate the covariance matrix, then calculate the eigenvectors, sort the eigenvectors by their eigenvalues, choose your n largest eigenvalues. So for example, if you wanted to go from 2 dimensions down to 1 dimension, you would choose your n is equal to 1 largest eigenvalue. So that ends up with 1 eigenvector, your 1 principal component. Then you project the original data onto the eigenvectors. All right, in the next lecture, we're actually going to manually implement this exact set of processes with code. I'll see you there.